A distant galaxy shaped like a tadpole holds 50 of the universe's most baffling secrets. This is the Tadpole Galaxy, a cosmic collection of oddities that defies our understanding of space. By the end of this journey, you will have explored 50 of its strangest phenomena, from mysterious repeating radio signals to structures that some believe could be alien in origin. How can a cloud of hydrogen drift completely alone through the void? And what is the true nature of a star that refused to die? Which of these cosmic puzzles do you think will be the hardest to solve? A powerful, repeating rhythm of radio waves pulses from the heart of the Tadpole Galaxy. This is the first of our 50 strange objects, an unidentified radio source that has left astronomers utterly perplexed. It was first picked up by a network of radio telescopes listening to the silent depths of space, a signal so persistent and so structured that it immediately stood out from the cosmic background noise. Its frequency patterns are the core of the mystery, pulsing in a sequence that does not match the behavior of any known star, pulsar, or collapsing gas cloud. The rhythm is too orderly to be easily dismissed as a natural phenomenon, yet its power is immense, emanating from a source that must be incredibly energetic. This has sparked a fierce and ongoing debate within the scientific community. Could this be the first faint whisper of an intelligence not our own? A deliberate beacon meant to announce a presence across the vast interstellar ocean? Or is it something perhaps more haunting? The final, malfunctioning transmission of a piece of technology so advanced we can barely comprehend its purpose. A cosmic siren call with no one left to hear it. The signal repeats, a question mark written in radio waves against the dark canvas of the Tadpole Galaxy, and we are only just beginning to listen. That persistent, rhythmic signal forces us to confront two radically different possibilities, each more incredible than the last. On one hand, astronomers propose it could be a natural engine of unimaginable power, a type of hyper-magnetized neutron star whose magnetic field is trillions of times stronger than anything in our own galaxy. Such an object could, in theory, produce focused beams of radio energy with a regularity that mimics a deliberate pattern. Yet, no known star of this type matches the signal's unique fingerprint, suggesting we may be witnessing an entirely new class of cosmic object, a celestial powerhouse whose physics we have yet to write. On the other hand, the signal's strange orderliness points toward a different, more profound explanation. Could this be what scientists call a technosignature, a detectable sign of technology built by an intelligence beyond Earth? It is not simply a message, but perhaps the faint background hum of a civilization's vast energy use, or an automated beacon left to run for eons. This is the core of the debate that now grips the search for extraterrestrial intelligence, known as SETI. The continued detection of the signal is what makes it so compelling. A one-off burst could be a cosmic accident, but a repeating rhythm implies a stable, enduring source. For SETI researchers, this is the ultimate test. It pushes them to refine their instruments, to separate the possible whisper of a distant technology from the roaring symphony of the natural universe. The Tadpole Galaxy has presented us with a riddle, and with every new pulse, it asks us the same question. Are we hearing the heartbeat of a new kind of star, or are we listening, for the very first time, to the echo of another mind? That signal is not the only orphan in the cosmic deep. Drifting through the void near the Tadpole Galaxy is an object so ethereal it can barely be seen, a colossal cloud of pure hydrogen gas that appears to belong to nothing at all. This is our second strange object, a ghostly hydrogen cloud of almost unimaginable scale. It stretches for tens of thousands of light years, a vast, lonely island of primordial matter in an ocean of nothingness. What makes this cloud so baffling to astronomers is its profound isolation. It is not orbiting a galaxy, nor is it the glowing trail left by a passing star. It simply exists, a solitary and immense structure of the most basic element in the universe, floating completely untethered in the intergalactic darkness. Its temperature adds another layer to the mystery. The cloud is surprisingly cold, far colder than the thin, hot gas that is known to exist between galaxies. This deep chill defies easy explanation, as such a large and diffuse cloud should be warmed by the faint background radiation that permeates all of space, or by the occasional cosmic ray. Its coldness suggests it is a relic, a pristine pocket of the ancient universe that has somehow remained undisturbed for billions of years. How could such a fragile structure survive for so long without being torn apart or heated up by gravitational forces or galactic winds? Its very existence challenges the rules of galactic formation. One leading theory suggests this cloud is the sole visible component of a failed galaxy, often called a dark galaxy. In this scenario, it is the remnant of a pocket of the early universe that simply did not have enough dark matter to pull itself together and ignite the fires of star formation. It is a cosmic ghost town, all the raw materials for a brilliant city of stars present and accounted for, but forever frozen in the initial construction phase. Another possibility is that it is the shredded remains of a smaller galaxy that was torn apart in a past collision with the Tadpole Galaxy itself, a galactic tide that pulled the stars away but left this immense veil of gas behind. If that is true, then this ghostly cloud is a silent witness to a violent, ancient event, a cosmic fossil that holds clues to the Tadpole Galaxy's own turbulent history. This lonely cloud forces us to ask what it truly takes to build a galaxy, and how many of these dark, silent failures might be drifting, unseen, in the voids between the stars. While that lonely hydrogen cloud wanders in silence, another object in the Tadpole Galaxy stages a dramatic and deceptive performance. This third strange object was first cataloged as a supernova, a star meeting its explosive end. But then it refused to follow the script. Unlike a true supernova, which flares brilliantly and then steadily fades into obscurity, this object has been flickering for decades. It dims almost to the point of vanishing, only to surge back to brightness again, behaving more like a stubborn ember than a final, catastrophic blast. This erratic cycle challenges one of astronomy's core beliefs, the finality of a supernova explosion. We thought we understood stellar death as a single, definitive event. This object, however, suggests a star can die in fits and starts, a process far more complex and drawn out than anyone predicted. So what could possibly be going on? One compelling theory proposes we are witnessing a zombie star. In this scenario, the star did undergo a massive eruption, blowing off its outer layers in a supernova-like blast. But somehow, the star's core survived the trauma. This reanimated corpse, a zombie star, continues to burn unstably, periodically ejecting more material and causing the strange, repeating brightening we observe. It is a star that experienced a near-death event, but did not fully die. Another explanation points to a different type of stellar monster, a luminous blue variable. These are immense, unstable stars prone to violent tantrums. They can shed colossal amounts of material in repeated eruptions over thousands of years, before they finally explode as a proper supernova. What we are seeing might not be one death, but a long and violent prelude, a series of massive outbursts that merely mimic the final act. Each theory paints a picture of stellar existence far more turbulent and unpredictable than we knew. This supernova impostor forces us to reconsider the very last chapters of a star's life, revealing a cosmos where even death itself is not always a simple, one-time event. Deep within the swirling tail of the Tadpole Galaxy lies a place where gravity itself seems broken. This is our fourth strange object, a region astronomers call the dark matter core. It is not an object you can see with any telescope, because it is made of something entirely invisible. Its presence is revealed only by its ghostly grip on the fabric of space. Light from galaxies billions of light years behind the Tadpole Galaxy travels toward us, but as it passes through this core, its path is warped. The light bends, not like a lens of glass, but like a lens of pure gravity, creating stretched and distorted mirages of the background galaxies. This effect, called gravitational lensing, is the universe's way of revealing its hidden architecture. The degree of bending is so extreme that it points to a single, shocking conclusion. There must be an immense concentration of mass in that core, a knot of gravitational force with almost no visible matter to account for it. This is the signature of dark matter, the mysterious, invisible substance that makes up most of the mass in the universe. By mapping how the light is bent, scientists can essentially trace the outline of this dark matter core, creating a map of the invisible. What they have found is profoundly strange. The core is not a simple, round blob. Its shape is lumpy and elongated, almost like a cosmic fingerprint. This unusual structure is a vital clue. If dark matter were made of fast-moving, lightweight particles, this dense knot should have smoothed itself out over time, becoming more spherical. The fact that it remains clumpy and distinct suggests that dark matter is what scientists call cold and slow-moving. This means its particles are likely heavy and sluggish, allowing them to clump together tightly into the intricate structures we see mapped through the lensing effect. This single, invisible core in the Tadpole Galaxy is more than just a cosmic oddity. It is a natural laboratory, testing our fundamental ideas about what holds the universe together. Every distorted image of a background galaxy is a data point, helping us read the nature of this shadow substance that dictates the fate of galaxies. The Tadpole Galaxy holds a key to the dark side of the cosmos, a key we are only just learning how to turn. A new kind of ghost haunts the outer halo of the Tadpole Galaxy, a solitary predator drifting through the darkness. This fifth strange object is a rogue black hole candidate, a stellar corpse that appears to be wandering completely alone, untethered from any star system or cluster. We cannot see the black hole itself, for it emits no light. Instead, its presence is betrayed by two distinct and brilliant pieces of evidence. The first clue was a faint, flickering point of X-ray light. When a black hole of this size drifts through a cloud of interstellar gas, its immense gravity pulls the gas inward. As this gas spirals down into the event horizon, it compresses and heats to millions of degrees, releasing intense bursts of X-ray radiation before it vanishes forever. This telltale X-ray flare was the initial hint that something massive and invisible was moving through the galactic outskirts. The second and more definitive piece of evidence came from a phenomenon called gravitational microlensing. As the black hole drifted in front of a distant, unrelated star, its gravitational field acted like a tiny, magnifying lens. For a brief period, the light from the background star warped and brightened in a very specific way. a signature that could only be caused by a dense, compact object with a mass several times that of our own Sun. The combination of these two signals, the X-ray whisper and the gravitational lensing flash, paints a compelling portrait of a lone wanderer. But how does a black hole end up so utterly alone? The story of its origin is one of cosmic violence. Most stellar mass black holes are thought to remain within the star clusters where they were born. This one, however, was likely ejected during a chaotic gravitational interaction. Picture a dense star cluster, a crowded stellar city. In its center, 3 stars might have become locked in a violent dance. When one of them collapses into a black hole, the complex gravitational forces can act like a slingshot, flinging the newborn black hole away at tremendous speed, casting it out into the galactic wilderness to roam forever. This rogue traveler is a fossil of that ancient chaos, a reminder that the birth of a black hole is not always a quiet affair, but can be a dramatic event that sends the darkest objects in the universe on solitary journeys through the void. While black holes stalk the darkness, another mystery radiates a faint cosmic warmth. A specific spiral arm of the Tadpole Galaxy emits a pervasive, ethereal glow that is invisible to our eyes but brilliant in the infrared spectrum. This is our 6th strange object, a mysterious infrared glow that blankets the region like a cosmic heat haze. Unlike the sharp, pinpoint light of stars, this glow is diffuse and spread across vast distances, a soft luminescence with no clear stellar source to power it. The energy must be coming from something else, something far more subtle and widespread. The secret to this gentle radiance lies in the nature of the light itself. Infrared light is essentially heat radiation, the kind of energy emitted by objects that are warm but not hot enough to shine with visible light. So what, in the cold of interstellar space, could be producing such a widespread and persistent warmth? The answer appears to be a cloud of complex organic molecules known as polycyclic aromatic hydrocarbons. These are not simple atoms of hydrogen or helium, but intricate carbon-based structures, sprawling mats of atoms arranged in rings and sheets. They are essentially the soot of the universe, the same kind of compounds you would find in the smoke from a candle flame or in the char on a piece of grilled food. When these delicate carbon mats are bathed in the ultraviolet light from young, hot stars, they begin to vibrate intensely, and this vibration causes them to release their excess energy as the very infrared glow we detect. They are acting like countless microscopic radiators, collectively warming that entire region of space. The presence of these molecules is a game changer for our understanding of the galaxy's chemistry. Carbon is the essential backbone of life as we know it, and these hydrocarbons represent some of the largest and most complex molecules ever found in deep space. Their widespread existence in the Tadpole Galaxy suggests that the fundamental building blocks for life are not rare or special to our own cosmic neighborhood. Instead, they appear to be a common byproduct of star formation and stellar death, scattered liberally across the galaxy. This leads to a tantalizing possibility. Could this faint infrared glow be more than just a chemical curiosity? Could it be the signature of widespread probiotic chemistry at work? We are likely witnessing the universe engaged in a kind of cosmic food preparation, laying out the basic organic ingredients on a galactic scale. These carbon rings are the raw flour and sugar for the recipe of life, and the Tadpole Galaxy's spiral arm is a vast, warm kitchen where these ingredients are being mixed and stored. It is not proof of life itself, but it is a powerful hint that the universe is fundamentally predisposed to creating the conditions for it. This gentle infrared hum is a whisper from the void, suggesting that the Tadpole Galaxy may be quietly, patiently, setting the table for a feast we have only just begun to imagine. Two brilliant furnaces blaze within the Tadpole Galaxy, pouring out more X-ray energy than should be possible. These are the twin ultraluminous X-ray sources, or ULKs, our seventh and eighth strange objects. They are not merely bright. They are impossibly radiant, shining with the power of millions of suns, yet all concentrated into a pinpoint of high-energy light. Each one is believed to be a binary system, a cosmic dance between a normal star and a stellar corpse, either a neutron star or a black hole. The immense brightness comes from the process of accretion, where the gravitational pull of the dense corpse is so strong it violently strips material away from its companion star. This stolen gas doesn't fall straight in. Instead, it spirals down into an incredibly hot, fast-moving disk that swirls around the central object, heating up to millions of degrees and glowing fiercely with X-rays before it crosses the point of no return. This is a familiar story in astronomy, but with these twins, the numbers simply do not add up. There is a fundamental limit in physics, called the Eddington limit, which dictates how brightly an object can shine before the sheer pressure of its own radiation blows the incoming material away, effectively turning off its own fuel supply. It is like trying to fill a bucket while a powerful fan is blowing the water back out. These twin ULXs break that limit. They shine dozens, even hundreds of times brighter than this theoretical maximum, as if their fuel is pouring in regardless of the cosmic fan trying to stop it. This defiance has forced astronomers to consider two radical possibilities. The first is that we are looking at a new class of black hole, one that is neither small nor supermassive, but something in between. An intermediate mass black hole with the mass of thousands of suns would have a much higher Eddington limit, allowing it to consume matter at a ferocious rate and produce the incredible brilliance we see. The second possibility is even stranger. What if the radiation isn't blowing outward in all directions, but is instead focused into a narrow, intense beam, like a cosmic lighthouse? If that beam just happens to be pointed directly at Earth, we would see an artificially high brightness, a trick of perspective that makes the object seem more powerful than it truly is. The debate over these twins is a debate about the fundamental rules that govern some of the most violent events in the universe. Are we witnessing the ravenous appetite of a middleweight monster, a black hole that could be a missing link in galactic evolution? Or are we being fooled by a brilliant illusion, a lighthouse beam from a spinning neutron star, sweeping across the void to momentarily blind our telescopes? The twin ULXs challenge our understanding of how matter behaves under the most extreme gravity, presenting a pair of brilliant, contradictory puzzles in the heart of the Tadpole Galaxy. Far from the brilliant chaos of the twin ULXs, a more elegant structure adorns the Tadpole Galaxy. It appears as a perfect string of cosmic jewels, a linear chain of intensely blue star clusters so perfectly aligned they form a celestial necklace. This is the string of pearls, our ninth strange object, and its flawless arrangement defies the typical swirling distribution of stars. These are not ancient suns, but stellar newborns, massive and brilliant, blazing with the fiery blue light of youth. Their perfect alignment is the real mystery, a straight line in a universe dominated by curves and spirals. How could nature produce such a geometrically perfect structure on such an immense scale? The answer lies in the invisible scaffolding of the cosmos. Astronomers theorize that these pearls formed sequentially along a single, incredibly dense filament of cold molecular gas. This gas filament, a cosmic river of raw star-making material, was likely compressed by a powerful shock wave that traveled through it like a ripple through water. This compression triggered a domino effect of star birth. As the wave moved along the filament, it squeezed the gas at different points, one after another, until the entire structure ignited into a series of brilliant stellar fires. The shock wave itself is a clue to a violent past. One of the most compelling ideas is that this wave was a direct result of a previous galactic interaction, the same event that likely stretched the Tadpole Galaxy into its current elongated shape. As another galaxy passed close by, its gravitational pull sent a titanic ripple through the tadpole's gas clouds. That ripple, traveling for millions of years, eventually encountered this specific filament and orchestrated the birth of every pearl in the chain. This makes the string of pearls more than just a beautiful sight. It is a fossilized record of an ancient collision, a living timeline of star formation. The youngest stars likely shine at one end of the chain, with their slightly older siblings arranged in sequence, marking the precise path the shock wave took. This stunning object provides one of the clearest visual examples of a process called triggered star formation, where one cosmic event sets off a chain reaction of stellar births. It reveals a universe where chaos and violence can give rise to structures of breathtaking order and beauty, a cosmic necklace forged in the aftermath of a galactic disaster. That cosmic necklace of star clusters is a testament to the immense forces that shape a galaxy, but sometimes those same forces can create a solitary projectile. Soaring through the Tadpole Galaxy is a massive blue-white star moving at a speed that defies belief. This is our 10th strange object, a high-velocity runaway, a stellar cannonball ejected from its birthplace, and now on a one-way trip into the void. It is an O-type star, a true titan among suns, dozens of times more massive and millions of times brighter than our own. Stars like this are not built for long lives or gentle journeys. They burn fiercely and die young, and this one is living its short life on the run. The sheer velocity of this star is the central mystery. It is moving so fast that it cannot be bound by the gravity of the region it now travels through. It is an escapee, a fugitive from its own stellar neighborhood. To achieve such a speed, it must have experienced a truly catastrophic launch event. The most likely scenario takes us back to a dense, chaotic star cluster, the kind of stellar nursery where such massive stars are born. In this crowded environment, gravitational encounters are violent and frequent. One compelling theory is that this star was once part of a tight binary system, orbiting a companion star. If that companion had gone supernova, the sudden, asymmetric explosion could have blown the entire binary system apart, violently ejecting the surviving star like a stone from a sling. The other leading idea involves a close gravitational encounter with another massive binary system in the cluster's core. In this cosmic dance, the interloping star could have been swung around the binary and flung away at tremendous speed, a gravitational slingshot effect that turned a star into a projectile. This runaway carries the signature of its violent past written in its motion. As it plows through the interstellar medium at such incredible speed, it creates a visible bow shock ahead of it, much like the wave that forms at the front of a speedboat. This glowing arc of compressed gas is a direct result of its supersonic travel, a permanent headlight announcing its passage through the galactic darkness. Its solitary journey raises a profound question about the destiny of such stars. It will live its entire, brilliant life in isolation, far from the cluster of its birth, and when it finally dies, its supernova explosion will light up an empty region of the galaxy, a spectacular funeral with no stellar witnesses. This runaway star is a stark reminder that the cosmos is not a placid place, but a dynamic arena where stars can be born in clusters and then violently scattered, sent on solo voyages that last until their final brilliant end. The engine at the heart of the Tadpole Galaxy is a monster of a different kind. This is our 11th strange object, the central supermassive black hole, a gravitational titan whose appetite is not constant, but comes in violent, unpredictable bursts. Unlike the dormant giant at the center of our own Milky Way, this one is wide awake and flickering, its brightness fluctuating wildly across the entire electromagnetic spectrum, from radio waves to high-energy gamma rays. These are not subtle changes. The galaxy's core can brighten by a factor of 10 in a matter of weeks, then just as quickly fade back into relative dimness. This erratic behavior is a direct window into the black hole's feeding habits. Imagine a bonfire where someone is not adding logs steadily, but instead throwing on entire trees at random intervals. The resulting flare-ups and dimming mirror what we see happening on a cosmic scale. The material spiraling into the black hole does not form a smooth, steady stream, but rather clumps and gathers into a chaotic, stampeding herd of gas clouds and dust. As these immense clumps of matter are torn apart and swallowed, they release colossal bursts of energy, causing the brilliant flares we detect. Even more dramatic are the powerful jets this activity can produce. Occasionally, the black hole does not just consume matter, it also violently ejects a portion of it. Twisted by powerful magnetic fields, some of the infalling material is channeled away from the poles at nearly the speed of light, forming two opposing beams of superheated plasma that can stretch for thousands of light years into intergalactic space. These jets are like cosmic blowtorches, carving through the surrounding gas and influencing the formation of new stars far beyond the black hole's immediate grasp. The very existence of these jets tells us that a supermassive black hole is not just a passive sinkhole, but an active and dynamic engine that can shape its entire galactic home. The tadpole's flickering heart reveals a fundamental truth about these cosmic giants. They are not silent sentinels, but messy, temperamental eaters, and their variable brightness is the universe's way of showing us the chaotic, clumpy nature of the final feast. The erratic flickering of the galactic core is dwarfed by a single, unimaginable flash from the galaxy's edge. An object in the Tadpole Galaxy produced one of the most powerful explosions in the universe. A gamma ray burst so brilliant it momentarily outshone the rest of the cosmos combined. But the real mystery is not the blast itself, it is what was left behind. This 12th strange object is the enigmatic gamma ray burst afterglow, a persistent remnant that has refused to fade away. For days, then weeks, and even months after the initial cataclysm, this fading ember continued to shine across the entire spectrum of light, from radio waves to X-rays. This lingering glow is the cosmic equivalent of a fire's heat still radiating from long-cooled ashes, and its unprecedented longevity has become a profound puzzle. Most gamma-ray burst afterglows fade rapidly, their light dying away as the expanding shockwave from the explosion thins out and cools. This one, however, has held on, its multi-wavelength glow persisting far longer than any standard model predicted. It is as if the fire is being stoked, its fuel replenished from an unexpected source. Astronomers are now confronted with two compelling explanations for this enduring light. The first possibility is that the central engine of the explosion was itself unusual. A typical gamma ray burst is thought to be caused by the collapse of a massive star into a black hole, or the merger of two ultra-dense neutron stars, events that are violent but brief. This event, however, might have created a magnetar, a newborn neutron star with a magnetic field quadrillions of times stronger than Earth's. This spinning magnetic powerhouse could have continued to pump energy into the expanding blast wave for an extended period, like a battery attached to the explosion, powering the long-lasting afterglow we see. The second theory points to the environment around the blast. Perhaps the star that died was embedded in an exceptionally dense cocoon of gas and dust, material it had shed in the millennia before its collapse. As the explosion's shockwave plows into this thick surrounding material, it continuously rams into new fuel, generating fresh emission, and keeping the afterglow bright for far longer than it would in empty space. This would be like a fire spreading through a damp forest, smoldering and flaring for a long time rather than burning out quickly in a dry field. Each observation of this fading light is a clue. By monitoring how the afterglow dims in X-rays compared to radio waves, scientists can essentially perform an autopsy on the explosion, determining the density of the surrounding material and the total energy of the original event. This stubborn afterglow is more than a fading echo. It is a detailed chronicle of a stellar death, written in light and radiation, forcing us to reconsider the final moments of the universe's most titanic stars. Two beautiful, ghostly orbs drift side by side in the Tadpole Galaxy, the final glowing breaths of dying stars. These paired planetary nebulae, our 13th and 14th strange objects, present a matched set of cosmic contradictions. They are the luminous shrouds of gas, brilliantly illuminated by the intense ultraviolet light from the tiny, hot stellar cores at their centers. Yet for all their visual harmony, their internal chemistry tells a deeply discordant story. Standard models of stellar evolution predict a specific recipe for these ejected shells, a mix of elements like hydrogen, helium, and carbon, the standard ashes of a star's nuclear furnace. But spectroscopic analysis of these two nebulae reveals a bizarre anomaly. They contain a surprising overabundance of much heavier elements, including neon and argon. These are not the typical products of a gentle, dying star. Their presence in such quantities is like finding forged steel inside a lump of coal, a clear sign that the processes which created these elements were far more violent and complex than anyone expected. How could these heavy elements have been forged and then ejected so efficiently? The answer may lie in a dramatic stellar partnership. One leading theory suggests that these stars were not solitary when they died. Each might have been part of a binary system where a close companion star, perhaps a white dwarf, transferred material back onto the dying star. This influx of fresh fuel could have triggered brief, explosive bursts of nuclear fusion right at the star's surface, a process known as a late thermal pulse. These pulses are like a final, furious stoking of the fire, producing unexpected heavy elements and then blasting them out into space, enriching the nebula with their strange chemistry. Another possibility points to the star's initial mass. They might have been significantly heavier than the typical stars that form planetary nebulae, crossing a mass threshold that allowed them to ignite neon and argon in their cores during their final frantic days. This would mean we are witnessing the death throes of a rare class of star, one that operates by a different nuclear rulebook. These two glowing ghosts are more than just pretty sights. They are celestial laboratories. Their unusual chemistry forces astronomers to rewrite the final chapters of stellar life, revealing that a star's death can be a messy, unpredictable affair. capable of forging and flinging exotic elements into the galaxy. They stand as a paired reminder that even in its last moments, a star can defy our expectations and reveal new, fundamental secrets about the universe's elemental recipe. A profound darkness resides in the Tadpole Galaxy, a void that somehow radiates an intense but invisible heat. This 15th strange object is a candidate for a dark star, a theoretical giant from the dawn of time that operates on a power source completely alien to modern stars. While every other star shines from the nuclear fusion in its core, crushing hydrogen into helium, this object suggests a different kind of fire. It is detected overwhelmingly in the infrared and sub-millimeter wavelengths, meaning it pours out immense warmth while emitting almost no visible light. It is a cosmic heater, not a cosmic lamp. This bizarre energy signature points to a radical possibility that the star's core is not powered by fusion at all, but by the annihilation of dark matter. In this hypothetical scenario, the star would be composed primarily of hydrogen and helium, but it would be suffused with a dense, concentrated cloud of dark matter particles. As these particles collide with their antimatter counterparts deep inside the star, they would annihilate, converting their mass directly into pure energy and heat, providing a steady, long-lasting glow that requires no nuclear reactions. A dark star would be a relic of the universe's first chapter, a behemoth that could grow to be millions of times more massive than our sun and shine for millions of years, all without ever igniting its nuclear furnace. Yet, there is a more conventional, though still exotic, explanation. This object could simply be a very young protostar, a stellar infant still swaddled in an incredibly thick, dark cocoon of gas and dust. In this case, the intense infrared glow is the heat from its gravitational collapse, trapped and reprocessed by the surrounding material. The reason we see no visible light is that the shroud is so dense that not a single optical photon can escape. Only the longer, more penetrating infrared waves can fight their way out. So how can we tell the difference between a cosmic fossil and a newborn sun? The key lies in the specific chemical fingerprints within its light. A true dark star, powered by gentle dark matter annihilation, would not produce the heavy elements that forge the spectral signatures of a protostar. Its environment would be pristine, uncontaminated by the complex chemistry that comes from nuclear fusion. Astronomers are now searching for these subtle clues, trying to decipher whether they are looking at a never-before-seen type of star from the beginning of everything, or simply the most obscured stellar nursery ever found. This dark candidate holds the potential to rewrite the story of how the first stars were born, suggesting that some may have lit up the early cosmos not with a flash of nuclear fire, but with the slow, steady burn of the universe's own shadow substance. Deep within the Tadpole Galaxy, two stellar titans are locked in a fatal, accelerating dance. This 16th object is a binary system of massive stars, two immense bodies whirling around a shared center of gravity at staggering speeds. Their orbital characteristics are what make them so extraordinary, a spiraling trajectory that tightens with every passing orbit. They are not merely circling one another, they are gradually falling inward, destined for a cataclysmic collision that will shake the very fabric of spacetime. Astronomers identified this pair as a prime progenitor for a future gravitational wave event by observing the subtle, rhythmic changes in their light. As the stars orbit, they periodically eclipse each other, and by measuring the precise timing of these eclipses, scientists can calculate their orbital period down to the second. The critical discovery was that this period is decreasing, imperceptibly but inexorably. The stars are losing orbital energy, and that energy is being carried away in the form of gravitational waves, the ripples in space-time predicted by Einstein. This slow cosmic drain is causing their inward spiral, setting the stage for a final violent merger. The sheer mass of these stars points to a specific and spectacular fate. When they finally collide, they are not expected to form a simple, larger star. Instead, their cores will likely combine to create a newborn black hole in an event so energetic it could also unleash a short gamma-ray burst, a blinding flash of high-energy radiation. But the true legacy of this collision will be forged in its aftermath, in a brilliant cosmic explosion known as a kilonova. A kilonova is more than just a flash of light. It is the universe's primary forge for the heaviest elements. The intense conditions during and after the merger, bombarded by a torrent of neutrons, allow for a process called rapid neutron capture. In this frantic environment, atomic nuclei grab hold of free neutrons at an incredible rate, building up elements far heavier than iron. It is here, in the aftermath of such a stellar death spiral, that gold, platinum, and uranium are thought to be created and then blasted out into the galaxy. This binary system is a ticking clock, counting down to the moment it will seed the Tadpole Galaxy with the very elements that make up our most precious metals, and even the radioactive fuel that heats the interior of planets. Without such violent endings, the periodic table would be a much emptier place. These two stars are more than just a future spectacle. They are a promise of cosmic creation, a reminder that the gold in a wedding ring or the uranium in a power plant was likely born from the explosive merger of two dead stars in a galaxy far, far away. A slender, brilliant crescent of light curves against the darkness, a galaxy stretched into a cosmic smile. This is the lensing arc, our 17th strange object, and it is not a galaxy within the tadpole at all, but a far more distant system whose light has been captured and warped on its journey to us. The Tadpole Galaxy's immense mass acts as a natural telescope, its gravity bending the fabric of spacetime around it. When light from a background galaxy travels through this warped region, its path is curved, creating multiple distorted images of the same object. In this case, the alignment is so perfect that the galaxy's image has been smeared into a nearly complete ring, a bright arc that wraps around the tadpole's dense core. This phenomenon, called strong gravitational lensing, is one of astronomy's most powerful tools. It allows us to see the otherwise invisible. The background galaxy is so incredibly far away that, without this cosmic lens, it would be nothing more than a faint, unresolved speck, even to our most powerful telescopes. The lensing effect does two miraculous things. First, it magnifies the galaxy's light, making it appear dozens of times brighter than it truly is. Second, it stretches the galaxy out, effectively zooming in and revealing details of its structure that would be completely lost across such a vast gulf of space. By analyzing the exact shape and brightness of this arc, astronomers can perform a kind of cosmic reconstruction. They can deduce the true shape of the background galaxy, calculate its distance with remarkable precision, and even map the distribution of stars and gas within its spiral arms. This single, curved line of light becomes a window into the early universe, allowing us to study a galaxy as it was when the cosmos was much younger. Every subtle kink and variation in the arc's brightness holds information, not just about the distant galaxy, but about the tadpole itself. The arc acts as a probe, tracing the precise distribution of both visible and dark matter in the lensing galaxy's core. It is a perfect example of cosmic synergy, where one deep space mystery is used to unravel the secrets of another, all through the subtle, universe-bending power of gravity. A cosmic heartbeat in the Tadpole Galaxy is skipping beats. This 18th strange object is an anomalous Cepheids variable, a type of star astronomers rely on as a fundamental yardstick for measuring the universe. Cepheids are the metronomes of the cosmos, pulsating with a clockwork regularity. Their pulse period is directly tied to their true brightness, a relationship so reliable that by measuring how fast one pulses and how dim it appears from Earth, we can calculate its distance with incredible precision. This one, however, is broken. Its rhythm has become erratic, its pulse period and brightness changing in an unpredictable, jittery dance that throws all its measurements into question. The very tool we use to map the cosmos has developed a flaw. So what could be causing this stellar arrhythmia? One strong possibility is that we are not looking at one star, but two. This Cepheid could be locked in a tight binary system with an unseen companion. The gravitational tug of this partner star would periodically pull the Cepheid slightly closer to us and then farther away, subtly altering the timing of its pulses and its apparent brightness in a way that looks like internal instability. It would be like trying to listen to a steady drumbeat from a car that is constantly accelerating and braking, the rhythm seeming to waver because of the motion, not the drummer. Another explanation points to turmoil within the star itself. Cepheids are in a late, unstable phase of their lives, and this one might be undergoing significant internal structural changes. The layers of helium and hydrogen in its outer shell could be sloshing around unpredictably, causing its nuclear furnace to stutter and flare. This would directly affect the pressure that drives the pulsations, leading to the erratic behavior we observe. A third, more exotic theory involves a circumstellar disk. The star might be surrounded by a thick, clumpy ring of dust and debris, the remains of a previous eruption or a captured cloud of material. As the star pulses, its light would shine through this uneven disk. Some pulses would be dimmed more than others as they pass through thicker clumps of dust, creating the illusion of unpredictable brightness changes from our distant vantage point. Each pulse of this anomalous star is now a data point in a new kind of mystery. Is it a binary impostor, a star in internal upheaval, or a beacon shining through a cosmic veil? The answer matters deeply, because if our standard candles are not so standard, we must recalibrate our maps of the universe, starting with the very galaxy they call home. Two galaxies are being torn apart before our very eyes, a pair of cosmic dancers caught in the Tadpole Galaxy's immense gravitational embrace. These two small, distorted galaxies, our 19th and 20th strange objects, are not neighbors of the Tadpole, but are instead in the process of merging directly with it. Their spiral arms, once elegant and symmetrical, are now stretched into long, shimmering streams of stars and gas. These are tidal tails, brilliant scars painted across the darkness by the raw force of gravity. As the trio of galaxies interacts, their gravitational fields pull and tug on each other, drawing out these immense rivers of material in a process that can take hundreds of millions of years. It is a slow-motion demolition, where the very fabric of the smaller galaxies is being unraveled and woven into the tadpole's growing form. Yet this destruction is also an act of creation. The collision is triggering a fireworks display of stellar birth. Within the chaotic piles of compressed gas, vast nurseries of new stars are igniting all at once. These are starburst regions, areas where star formation is happening at a ferocious rate, hundreds or even thousands of times faster than in a quiet galaxy like our own Milky Way. The trigger is simple yet violent. When giant clouds of gas are slammed together by the galactic collision, they are suddenly and violently compressed. This rapid increase in density pushes the gas over a critical threshold, forcing it to collapse under its own gravity and ignite into brilliant new suns. This provides a live-action view of the processes that built the galaxies we see today. We are witnessing, in real time, the same kind of event that likely shaped the Tadpole Galaxy's own spectacular tale in the distant past. It is a cosmic feedback loop, where galactic mergers trigger star formation, which in turn enriches the galaxy with new elements, paving the way for future generations of stars and planets. This interacting pair is a living fossil, a direct window into the universe's most formative and dramatic events. A perfectly round pocket of nothingness punctuates one of the Tadpole Galaxy's spiral arms. This 21st strange object is an empty void, a spherical region of startling emptiness that spans hundreds of light years. It is not just a sparsely populated area, but a cosmic clearing of profound darkness, a perfect bubble that contains almost no stars, no glowing nebulae, and very little of the gas required to form new ones. Its geometric perfection is the first clue that this void was not formed by random chance. Such a clean, spherical emptiness suggests a powerful, focused event that swept the region clear. The most likely architects of this void were the very stars that once filled it. Imagine a generation of stellar titans, dozens of massive, short-lived stars born together in a tight cluster. These stars do not live gently. They burn through their nuclear fuel in just a few million years. And during their brief, brilliant lives, they rage against their surroundings. They emit powerful stellar winds, torrents of charged particles that stream outward at millions of miles per hour, like a constant cosmic hurricane. This relentless gale begins to push the surrounding interstellar gas and dust away, slowly carving out a cavity in the stellar nursery. Then, one by one, these massive stars reach the end of their lives and explode as supernova. Each explosion is a cataclysmic final act, unleashing a shockwave of unimaginable force that slams into the gas already being blown away by the surviving stars. This combination of winds and repeated supernova blasts acts like a team of cosmic bulldozers, efficiently clearing out every last trace of star-forming material from a vast spherical volume. The void we see today is the fossilized remnant of that ancient stellar violence, a bubble blown in the galactic disk by the collective final breaths of an entire generation of stars. There is, however, a more exotic and puzzling possibility. Could this spherical emptiness have been punched into the galaxy by something completely invisible? Astronomers theorize that it might be the scar from a past encounter with a dense knot of dark matter, a subhalo. These invisible clumps of dark matter are thought to pepper galaxies, and if one passed directly through this spiral arm, its intense gravitational field could have scattered the stars and gas in its path, pulling them away and leaving behind a temporary, starless void in its wake. The spherical shape would be a natural result of the encounter's geometry. Whether carved by fire or sculpted by shadow, this empty void stands as a stark reminder of the immense forces that can shape a galaxy, creating pockets of pure nothingness where a thriving stellar community once existed. A different kind of signal cuts through the galactic static, a brilliant, focused beam of microwave light shining like a celestial lighthouse. This is the methanol megamaser, the 22nd strange object in our collection, and it is a natural laser of almost unimaginable power. The word maser stands for microwave amplification by stimulated emission of radiation, and while that sounds complex, the concept is akin to a laser, but operating at microwave frequencies instead of visible light. This particular cosmic beam is generated by clouds of methanol molecules, the same simple alcohol found on Earth, swirling in regions of frantic stellar birth. The intense ultraviolet radiation and powerful shock waves from newborn, massive stars provide the energy that pumps these molecules, exciting them into a higher energy state. When a passing microwave photon of the right frequency strikes one of these excited molecules, it triggers a chain reaction, stimulating the molecule to release an identical photon. These photons then travel in perfect lockstep, creating an intense, coherent beam of microwave radiation that can be detected across intergalactic distances. This megamaser is more than just a cosmic curiosity. It is an invaluable tool for galactic cartography, because the methanol emission occurs at a very specific and stable frequency. Any slight shift in that frequency due to the Doppler effect reveals the precise velocity of the gas cloud along our line of sight. By mapping the velocities of these megamasers across different parts of the Tadpole Galaxy, astronomers can construct a three-dimensional model of its rotation and internal motions. It is like placing thousands of tiny, precise speedometers throughout the galaxy's spiral arms, allowing us to see how fast each section is moving and in which direction. This data helps scientists weigh the galaxy, calculate the distribution of its dark matter, and understand the gravitational forces that are shaping its iconic tadpole form. This natural laser, born from the chaos of a stellar nursery, becomes a precise instrument, illuminating the hidden dynamics of an entire galaxy. Another rhythm cuts through the galactic noise, a series of millisecond-long screams of pure energy. This is the fast radio burst repeater, our 23rd strange object, a source that has erupted not once, but multiple times with bursts of radio waves so intense they outshine entire galaxies for the briefest of moments. Each burst is a transient flash, a cosmic strobe light blinking on and off in a fraction of an eye blink, releasing more energy than our sun does in 80 years. The sheer power is staggering, but the fact that it repeats is what makes this source in the Tadpole Galaxy a game-changer for astronomers. Most fast radio bursts are one-off events, isolated shrieks in the dark that vanish before we can pinpoint their origin. This repeater, however, gives us a second chance, and a third, and a fourth. We know exactly which galaxy it calls home, and that single piece of information helps us solve a piece of the puzzle. The leading suspect for creating such violent, focused bursts is a magnetar, a type of neutron star with a magnetic field so powerful it could erase a credit card from half the moon's distance away. These stars are cosmic powerhouses, and when their immense magnetic fields undergo a sudden rearrangement, a starquake, they can crack their rigid crusts. This seismic event is thought to launch a titanic shockwave through the magnetar's surrounding environment, which in turn accelerates particles to near light speed, generating the blinding flash of radio waves we detect as a fast radio burst. The repeating nature suggests these starquakes are not a one-time cataclysm, but recurring events on a hyper-magnetized stellar corpse. Yet, the repeater's location within the Tadpole Galaxy helps us rule out other, more exotic explanations. Because we can identify its host galaxy, we know it is not coming from an impossibly distant source whose light has been warped beyond recognition. We know the environment is a stellar one, not the void between galaxies. This allows astronomers to confidently dismiss theories involving the evaporation of primordial black holes or the violent mergers of exotic objects in the empty cosmic deserts. Every new burst from this source is another data point, another clue to the inner workings of the most magnetic objects in the universe. It is as if the Tadpole Galaxy has handed us a living laboratory, a magnetor we can watch and study each time it unleashes its pent-up fury, bringing us closer than ever to understanding the true nature of these brilliant, fleeting cosmic mysteries. Nestled within the Tadpole Galaxy's halo is a dense, ancient sphere of stars that defies the standard cosmic timeline. This is an unusually metal-rich globular cluster, our 24th strange object. Globular clusters are typically the universe's oldest fossils, pristine balls of stars that formed when the cosmos was young and filled with little more than hydrogen and helium. Their stars are notoriously metal-poor, meaning they contain only trace amounts of elements heavier than helium, forged in the hearts of long-dead stars. This particular cluster, however, shines with a surprising chemical signature. Its starlight reveals an abundance of heavier elements like oxygen, carbon, and iron, metals that should not exist in such an ancient relic. This high metallicity is a profound contradiction, a historical document that seems to have been written with ink from the wrong era. So why does this ancient cluster look so modern? One compelling theory suggests it is not as old as its counterparts. It may have been one of the last globular clusters to form in the galaxy, condensing from a pocket of gas that had already been seeded with heavy elements by earlier massive stars. In this scenario, it is not a first-generation pioneer, but a second-generation successor, born from the ashes of its predecessors. Another possibility is even more transformative. The cluster might have formed early, but in an exceptionally dense and fertile region of the early Tadpole Galaxy. If the very first stars in that region were incredibly massive and short-lived, they could have exploded as supernova in a rapid, concentrated wave, polluting the surrounding gas with metals almost instantly. This newly enriched gas would then have collapsed to form this cluster, making it a first-generation object with a chemical makeup that mimics a much later birth. This single cluster forces astronomers to rethink the pace of chemical evolution in the early universe. It reveals that the cosmos may not have been a uniformly primitive place, but rather a patchwork of environments where some pockets matured into chemical complexity far faster than others. This ancient, metal-rich ball of stars is a time capsule with a scrambled date, challenging our most fundamental assumptions about how and when the universe built its first cities of suns. From the chaos of galactic destruction, new worlds are born. These twin tidal dwarf galaxies, our 25th and 26th strange objects, are not being torn apart, but are instead coalescing from the wreckage. They are condensing within the immense tidal tail of gas and dust that streams away from the Tadpole Galaxy, a river of raw material forged in a past collision. Picture a sculptor carving two new statues from the chips and shavings of a larger, broken masterpiece. That is the essence of these forming galaxies. They are cosmic recycling in its most literal form, entire island universes being built from the scattered debris of a galactic accident. This process begins when the gravitational turmoil of a collision flings vast amounts of gas and stars out in the void. This material doesn't just dissipate. Instead, within the long tidal streamers, pockets of gas can become so dense and massive that their own gravity takes over. They begin to collapse inward, pulling and surrounding dust and stars, slowly knitting themselves into a coherent, self-gravitating structure. It is a bottom-up creation, where a cloud of cosmic rubble decides to become a city. What is so fascinating about these twins is their potential for independence. Right now, They are still connected to the tadpole by a thin bridge of material, like newborns connected by an umbilical cord. But as they continue to gather mass and condense, their own gravitational pull will strengthen. Eventually, that bridge will thin and snap, and these two objects will be set adrift as fully fledged dwarf galaxies, orbiting the tadpole as permanent satellites. They are not primordial objects from the dawn of time, but second-generation galaxies, born from the remains of their predecessor. Their stellar populations will be a mixed bag, containing both ancient stars stolen from the original galaxies and brilliant new suns ignited from the freshly compressed gas. This means they could potentially host planetary systems and, one day, even life, all built from the salvaged materials of a cosmic crash. The existence of these twins challenges the old idea that all galaxies formed in the early universe. It shows us that galaxy formation is an ongoing process, and that even today, new galactic entities can be forged in the violent, creative fires of a collision. A steady, rhythmic pulse of X-rays echoes from a binary star system deep within the Tadpole Galaxy. This is the 27th strange object, an X-ray binary with a cosmic heartbeat, a pair of stars locked in an orbit so intimate their interaction produces a predictable, repeating flash of high-energy light. The system consists of two mismatched partners, a normal star like our Sun and a dense stellar corpse, either a neutron star or a black hole. They orbit each other so closely that the immense gravity of the compact object relentlessly pulls a stream of gas from the outer layers of its stellar companion. This stolen material does not fall directly onto the surface. Instead, it forms a spinning, superheated disk of plasma called an accretion disk, whirling around the dense core at nearly the speed of light. It is within this swirling vortex of doomed matter that the heartbeat originates. The compact object at the center possesses an incredibly powerful magnetic field. This field acts like a rigid cage, preventing the incoming gas from reaching the surface everywhere except at the magnetic poles. As the material in the inner edge of the accretion disk builds up, it becomes funneled along these magnetic field lines, crashing down onto the poles in two focused, incredibly hot columns. Each time a massive clump of this superheated gas slams onto the surface, it releases a brilliant burst of X-rays, a flash of energy that marks one beat of the system's heart. The clockwork regularity of these pulses is the key to unlocking the system's deepest secrets. By measuring the precise period of the X-ray flashes, astronomers can calculate the orbital speed and distance between the two stars with astonishing accuracy. The strength and pattern of the heartbeat reveal the intensity of the magnetic field gripping the compact object, telling us whether it is a highly magnetized neutron star or a more placid black hole. Even the slight Doppler shift in the timing of the pulses as the compact object moves toward us and then away in its orbit allows scientists to weigh both stars in the system. This rhythmic X-ray source is more than a celestial metronome. It is a detailed diagnostic tool. Each pulse is a direct probe into the physics of extreme gravity and magnetism, a heartbeat that charts the vital signs of a stellar partnership defined by theft and violence. A tiny, brilliant emerald glows within the vast swirl of the Tadpole Galaxy. This 28th strange object is a local analog of a green pea galaxy, a compact and ferociously active region of star formation that shines with an unusual greenish tint in certain astronomical images. That distinctive color is not a trick of the light, but a direct signature of its violent stellar birth. The green hue arises from intensely bright emission lines of doubly ionized oxygen, a specific fingerprint of gas that has been blasted by a torrent of ultraviolet radiation from countless newborn massive stars. It is the cosmic equivalent of a neon sign, screaming the presence of a stellar nursery in overdrive. This small, greenish knot is far more than a colorful curiosity. It is a living fossil. Astronomers first identified entire galaxies with this signature in the distant early universe, calling them green P galaxies for their small, round, and green appearance in survey images. They were engines of creation, churning out stars at a rate hundreds of times faster than our own Milky Way, and they played a crucial role in heating and ionizing the primordial cosmos. The incredible discovery within the Tadpole Galaxy is that it holds a nearby example of this same frenzied process. We are witnessing, in our own cosmic backyard, the same kind of stellar firestorm that was commonplace billions of years ago. What makes this region so potent is its compactness. All this frantic star formation is crammed into a volume just a tiny fraction of the size of the entire galaxy. This creates a perfect feedback loop. The massive stars are born so close together that their combined ultraviolet radiation and powerful stellar winds violently heat and compress the surrounding gas clouds. This compression then triggers the next wave of star formation in a self-perpetuating cycle of cosmic violence. The region is essentially turning its own gas into stars at a breakneck, unsustainable pace, a frenzy that will likely consume all its available fuel in a relatively short cosmic time. Finding this green P analog so close to home is a gift to science. It allows us to study the mechanics of early universe star formation with a level of detail impossible for its distant cousins. We can resolve individual star clusters within it, measure the velocities of its gas, and understand how these stellar powerhouses evolve. This tiny green dot is a time machine, offering a front row seat to the conditions that built the first galaxies and lit up the dark, early cosmos with the fires of new suns. A lopsided ghost of a stellar cataclysm drifts through the Tadpole Galaxy, its form a frozen echo of violence. This 29th strange object is an asymmetric supernova remnant, an expanding shell of stellar debris that should be a near-perfect sphere, yet it stretches into a ragged, one-sided blossom. The death of a star is one of the most symmetric explosions imaginable, a shock wave blasting outward in all directions. So why does this particular corpse wear such a distorted shroud? The answer lies in the environment the explosion encountered. A supernova remnant expands not into a perfect vacuum, but into the clumpy, uneven interstellar medium. If the dying star was positioned near a particularly dense cloud of gas and dust on one side, the expanding shockwave would have slammed into that resistance like a wave hitting a seawall. The remnant's expansion would be dramatically slowed on that dense side, while it continued to balloon out freely into emptier space on the other, creating the lopsided shape we see today. It is a fossilized imprint of the galactic neighborhood the star inhabited in its final moments. Another possibility involves the corpse itself. At the heart of this remnant should be a neutron star, the ultra-dense core left behind by the supernova. If the explosion was slightly off-center, the same physics that causes a rifle to recoil when fired could have sent this stellar cannonball hurtling through space. This natal kick, imparted at birth, would have sent the neutron star rocketing away in one direction, while the bulk of the expanding debris shell flew outward in the other. We would be left with a remnant that is not centered on its own progenitor, a telltale sign of a violent and uneven birth. The most extreme explanation, however, points to the very nature of the star's death. Some supernova are not simple, spherical detonations. They are jet-driven, focused events where the star's collapse channels immense energy into two narrow beams erupting from its poles. If one of these jets was significantly more powerful than the other, or if we are viewing the remnant from an angle, it would appear profoundly asymmetric, sculpted not by its surroundings, but by the intrinsic directionality of its own death throes. This lopsided cloud is more than a celestial curiosity. It is a forensic snapshot. Its shape holds clues to the star that died, the density of the space around it, and the chaotic physics of stellar collapse. A single, frozen moment from a billion-year-old explosion that is still telling its story. Two clouds of gas race through the Tadpole Galaxy at impossible speeds, cosmic fugitives defying the stately rotation of their home. These high-velocity molecular clouds, our 30th and 31st strange objects, are not wispy veils of hydrogen but dense, compact knots of molecular gas, the very raw material for building stars. They are moving hundreds of kilometers per second faster than the galaxy's spiral arms, suggesting they were violently launched from their place of origin and are now on chaotic, high-speed journeys. Their existence points to a dramatic past, a moment of immense energy that could have only come from one of two cosmic engines. The first suspect is the galaxy's own active core. The tadpole's supermassive black hole, in one of its feeding frenzies, could have blasted out titanic jets of energy. While these jets are made of plasma, they can act like a cosmic snowplow, pushing and accelerating vast reservoirs of cold molecular gas that lie in their path out of the galactic center and into the halo. This would be like a volcanic eruption blasting boulders high into the atmosphere, except here the boulders are entire clouds of star-forming material, and the volcano is a black hole. The second, equally compelling theory traces their origin to the galaxy's long, streaming tail. These clouds might not be outbound projectiles, but inbound debris. They could be the leftover wreckage from the ancient galactic merger that shaped the tadpole massive clumps of gas that were flung far out during the collision, and are now, billions of years later, finally falling back into the main galaxy at tremendous velocities. They are cosmic boomerangs, returning from a journey that began with a violent encounter in the distant past. Regardless of their origin, their high-speed travel has a profound effect on their destiny. The normal, gentle collisions between gas clouds that trigger star formation are replaced by violent, high-energy impacts. This can either shred the clouds entirely, preventing stars from ever forming, or compress them so suddenly and fiercely that it ignites a firestorm of chaotic, massive star birth. These rogue clouds are testaments to the Tadpole Galaxy's turbulent life, either as scars from its hungry heart or as returning exiles from its most formative trauma. The very heart of the Tadpole Galaxy has a split personality. This 30-second strange object is a changing-look active galactic nucleus, a region where the central supermassive black hole appears to don a disguise and then remove it again. We have watched it transform from a brilliant quasar, shining with the power of a trillion suns, into a much quieter, dimmer state, all within a cosmic blink of an eye. Such a radical shift in appearance over just a few years defies our traditional view of these monsters as slow, steady giants. The leading explanation for this cosmic costume change lies in the black hole's dinner plate. The transformation is likely driven by a sudden and dramatic shift in the rate of gas accretion, the flow of materials spiraling into the black hole's maw. Picture a bonfire. When you steadily feed it wood, it burns with a constant bright flame. But if you suddenly dump a massive pile of logs onto it, the fire might flare up spectacularly before settling into a smoky, choked state. Conversely, If you abruptly cut off the fuel supply, the bright flame will quickly die down to embers. That is precisely what we think is happening here. A large, unstable clump of gas, perhaps from a shredded star or a disrupted gas cloud, may have wandered too close. When this clump was suddenly devoured, it caused a temporary but brilliant flare, making the nucleus look like a hyperactive quasar. Once that clump was consumed, the fuel supply dropped, and the core returned to its quieter state. This behavior reveals that the process of feeding a supermassive black hole is not a smooth, continuous stream, but a chaotic, clumpy, and unpredictable downpour. The changing look nucleus shows us that even the most powerful engines in the universe can be temperamental, flickering between brilliance and shadow based on the whims of their cosmic menu. A solitary beacon of pure power flashes in the galactic darkness, a neutron star completely divorced from the scene of its violent birth. This 33rd strange object is an isolated magnetar, a stellar corpse whose magnetic field is the strongest known force in the entire universe, trillions of times more powerful than Earth's. It spins slowly, completing a rotation only once every 10 seconds. A ponderous turn for a stellar remnant that should be whirling at dizzying speeds. With each rotation, it unleashes a storm of high-energy radiation, powerful bursts of X-rays and gamma rays that rip through the surrounding void. Its isolation is the central mystery. Magnetars are born in the supernova explosions of massive stars, and those cataclysms usually leave behind a glowing, expanding cloud of debris, a supernova remnant that cradles the newborn neutron star for thousands of years. This magnetar, however, floats in pristine emptiness. There is no remnant, no trace of the gaseous shroud that should mark its origin. It is a cosmic orphan, a child of violence that has wandered far from its cradle. How did it escape its own past? The most likely explanation is a natal kick of unimaginable force. When the star's core collapsed, the supernova explosion may have been profoundly asymmetrical. This imbalance would have acted like a rocket engine, violently ejecting the newborn magnetar from the center of the remnant at hundreds of kilometers per second. Over thousands of years, it simply traveled beyond the boundaries of the fading gas cloud, leaving the evidence of its birth far behind. Another possibility is that the original supernova remnant was exceptionally faint and diffuse, dissipating into the interstellar medium so quickly that it vanished long before our telescopes could ever hope to see it. This isolated magnetar is a pristine laboratory for studying the limits of matter. Its slow spin is a crucial clue, telling us that its immense magnetic field acts as a powerful brake, siphoning away the star's rotational energy and converting it into the violent radiation bursts we observe. By monitoring its gradual spin down, astronomers can directly measure the strength of this cosmic magnet and test theories about the behavior of matter under conditions so extreme they cannot be replicated on Earth. This lonely, flashing sentinel reminds us that the death of a star is not a tidy event, but a chaotic process that can send the most magnetic objects in existence on solitary journeys across the galaxy. A star in the Tadpole Galaxy is staging a rebellion against its own existence. This luminous blue variable, our 34th strange object, is a true stellar titan, so massive and volatile that it periodically tears itself apart in colossal eruptions. It has now entered a violent phase, brightening to become one of the single most luminous points of light in the entire galaxy, outshining millions of its neighbors combined. This is not the gentle flicker of a variable star, but a full-scale stellar tantrum, a paroxysm of energy so intense it blasts the star's own outer layers into space. These eruptions are not mere flares, they are mass-shedding events on an almost unimaginable scale. With each outburst, the star ejects a quantity of material equal to the mass of several planet Earths, or even an entire Jupiter, hurling it outward at speeds of millions of miles per hour. This creates a vast, expanding shell of glowing gas around the star, a temporary nebula forged from the star's own flesh. Why would a star behave in such a self-destructive manner? The core of a luminous blue variable is a battlefield where the outward pressure of radiation fights a desperate war against the inward crush of gravity. For most of a star's life, these forces are balanced, but in these hypermassive stars, the balance is incredibly fragile. The radiation produced in the core is so intense that it makes the star's outer layers buoyant and unstable. They begin to churn like a pot of boiling water, and eventually the radiation pressure wins, violently pushing huge sections of the star's atmosphere out into space, temporarily easing the internal pressure. Then the cycle begins anew. These stars are living on borrowed time, and their dramatic eruptions are considered a potential prelude to an even more spectacular end. A luminous blue variable is a prime candidate for a future supernova, a core collapse explosion that would outshine the galaxy for a brief, glorious moment. Some astronomers theorize that the most massive luminous blue variables could even be the progenitors of hypernova, supernova on steroids that are associated with the birth of black holes and the production of long-duration gamma-ray bursts. These are the most energetic explosions in the universe since the Big Bang itself. So when we watch this star in its eruptive state, we are likely witnessing the final, turbulent chapters of its life. It is a star screaming its existence in the void, shedding its skin in a series of violent farewells before it ultimately consumes itself in a final, cataclysmic fire. Two swirling nurseries of newborn worlds orbit young stars in the Tadpole Galaxy. These protoplanetary disks, our 35th and 36th strange objects, are not featureless rings of dust, but dynamic structures etched with their own miniature spiral arms. They look like tiny, glowing versions of the grand spiral galaxies they inhabit, a beautiful echo of form across vastly different scales. These spirals are not merely decorative, they are active construction zones, the very cradles where planets are being assembled from cosmic raw materials. The presence of these spiral arms reveals a disk in a state of gravitational turmoil. As the disk of gas and dust rotates around its central star, it can become so massive and dense that its own gravity begins to overwhelm the forces trying to keep it in a smooth, flat orbit. This imbalance causes the disk to fragment, collapsing into these distinct spiral waves. These waves act like cosmic traffic jams, compressing the gas and dust as they sweep through the disk. Within these compressed regions, tiny dust grains are more likely to collide and stick together, beginning the long process of growing from microscopic specks into full-size planets. This is the primary method for building gas giants, like Jupiter or Saturn, in a relatively short amount of cosmic time. Yet gravity is not the only sculptor at work. A second, equally compelling force could be carving these spirals: the gravitational pull of planets that have already formed. Imagine a newborn, Jupiter-sized planet embedded deep within the dark disk. As it orbits its star, its gravity would plow through the surrounding gas and dust, much like a speedboat creates a wake in water. This gravitational wake would manifest as a bright spiral arm, a direct and observable signature of an unseen world. In fact, multiple arms could point to multiple planets, each stirring the disk and shaping its own spiral pathway. These two disks offer us a direct window into the earliest stages of a solar system's life. We are not looking at a finished product, but at the dynamic, chaotic process of creation itself. The spirals are the chisel marks left on the raw stone of the disk, revealing whether the primary artist is the disk's own inherent instability or the hidden hands of newborn planets. By studying their precise shapes and rotations, we can effectively read the blueprint for an entire planetary system, watching as the Tadpole Galaxy forges new worlds from the dust of ancient stars. A different kind of ghost haunts the Tadpole Galaxy, an orphaned afterglow from a cataclysm we never saw. This 37th strange object is a lingering, multi-wavelength glow that appeared without the brilliant flash of a gamma ray burst to herald its arrival. It was as if scientists walked into a room to find only the lingering warmth of a fire that had already gone out, the main event completely missed. The absence of that initial, blinding signal is the core of the mystery. One compelling explanation is that we witnessed a gamma ray burst from the side, an off-axis event. These titanic explosions are not symmetrical. They channel their unimaginable energy into two narrow, relativistic jets that scream out from the poles of the collapsing star or merging neutron stars. If one of these jets is pointed directly at Earth, we see the full, spectacular fury of the gamma ray burst. But if the jet is angled away from us, we miss the main show. We would not see the initial flash, only the secondary effects. As the jet slams into the surrounding interstellar material, it creates a shockwave that heats up and glows across other wavelengths, producing the very afterglow we detected. It is like hearing only the echo of a shout from someone who has their back turned to us. The other possibility is that this orphan represents an entirely new class of cosmic explosion. Perhaps it was the result of a neutron star merger where the jets were choked off or failed to form properly, releasing their energy in a less focused, more spherical explosion that simply did not produce a bright gamma ray signal. Or maybe it was a tidal disruption event, where a star was shredded by a black hole, but under conditions so unusual that the usual electromagnetic fireworks were suppressed. This orphan afterglow forces astronomers to listen more carefully to the cosmos, to pay attention not just to the brilliant flashes, but to the faint, lingering whispers that follow. It suggests that for every cosmic cataclysm we see head-on, there may be dozens happening just out of view, their stories told only by the fading light they leave behind. A star in the Tadpole Galaxy is turning its own atmosphere into a cosmic chemistry set. This 38th strange object is a carbon star, an ancient, cool giant whose outer layers have become a factory for some of the most complex dust grains ever detected. Unlike most stars, which have more oxygen than carbon in their atmospheres, this one has flipped the cosmic recipe. Through nuclear fusion in its final stages of life, it has dredged up massive amounts of carbon from its core, enriching its outer layers with this fundamental element of life. Now, as it gently sheds its atmosphere in a slow, stellar wind, that carbon is condensing into solid particles in the cold of space. The starlight passing through this dusty shroud carries a unique chemical fingerprint, a spectroscopic signature that reveals the exact composition of these newly forged grains. Astronomers have identified the distinct spectral lines of silicon carbide, a hard, crystalline compound rarely found in such abundance. It is the same material used in some industrial abrasives on Earth, but here it forms naturally in the frigid vacuum around a dying star. The presence of such a specific and complex compound tells a profound story about the star's internal conditions. The temperature and pressure in its expanding atmosphere must be in a perfect, narrow range for carbon and silicon atoms to link up in this orderly, crystalline structure instead of forming simpler, amorphous soot. This single type of dust grain is a direct probe into the star's final stages of nuclear alchemy, but the chemical diversity does not stop there. Other spectral lines hint at even more exotic compounds, carbon chains, and molecules that are the precursors to the organic chemistry we associate with life. This stellar wind is not just ejecting simple atoms. It is manufacturing a rich inventory of complex materials. Each dust grain is a tiny time capsule, preserving a snapshot of the precise physical conditions inside a star during its death throes. When this star finally ends its life and expels its remaining layers as a planetary nebula, this unique dust will be blown out into the interstellar medium. It will eventually become part of new molecular clouds and later new solar systems. The silicon carbide and other complex grains forged in this star's atmosphere could one day be incorporated into asteroids, comets, and perhaps even rocky planets orbiting a future sun. This means the carbon star is not just an endpoint. It is a vital source of the raw, pre-processed materials needed for future cosmic construction projects, seeding the galaxy with the intricate chemical building blocks that make more complex structures, and perhaps even life, possible. A star's final, agonizing scream echoes across the electromagnetic spectrum. This 39th strange object is the aftermath of a tidal disruption event, a cataclysm that begins when a sun, on a random orbit through the galaxy, drifts too close to the central supermassive black hole. The star does not simply fall in. Instead, it experiences the black hole's tidal forces, a difference in gravitational pull so extreme that the side of the star nearest the black hole is tugged with immensely more force than the far side. This stretches the star horizontally while compressing it vertically, pulling it apart like a piece of cosmic taffy until it is shredded into a long, thin streamer of superheated gas. This process, called spaghettification, turns a once proud star into a swirling river of doomed matter. The black hole does not consume this streamer all at once. Roughly half of the stellar debris is flung away in the darkness, while the rest settles into a frantic, chaotic accretion disk, orbiting the event horizon at a significant fraction of the speed of light. As this gas spirals inward, it is compressed and heated to temperatures of millions of degrees, causing it to shine with a brilliant flare of radiation that can outshine the galaxy's core for months. What makes this event so valuable to scientists is the specific pattern of this flare. The light curve, the way the brightness rises and falls over time, acts as a cosmic clock and a scale. The time it takes for the flare to reach its peak brightness and then decay is directly related to the mass of the disrupted star and the mass of the black hole itself. A more massive black hole will shred a star at a greater distance, producing a brighter flare that takes longer to fade. By carefully analyzing this light curve, astronomers can effectively weigh the invisible monster at the galaxy's heart. Furthermore, the spectrum of the emitted light, from X-rays to radio waves, serves as a probe of the black hole's immediate environment. It reveals the composition of the devoured star, the density and structure of the newly formed accretion disk, and even the presence of powerful magnetic fields or relativistic jets that might be launched during the feast. Each tidal disruption event is a short-lived but incredibly detailed autopsy of a star's death, providing a rare and precious opportunity to measure the properties of a supermassive black hole and understand the violent physics that govern its dark domain. Two faint, cool embers drift together in the vastness, a pair of cosmic failures that defy simple classification. These binary brown dwarfs are our 40th and 41st strange objects, celestial bodies caught in a perpetual identity crisis. They are too massive to be considered true planets, yet they lack the critical mass needed to ignite the stable hydrogen fusion that defines a star. They are the failed stars of the Tadpole Galaxy, forever stuck in a dim, lukewarm state. Their discovery was only possible through the penetrating eyes of infrared telescopes, instruments designed to see the warmth of the cosmos rather than its brilliant light. Invisible wavelengths, these dwarfs are nearly invisible, but in the infrared, they glow with their own subdued thermal radiation, revealing a binary partnership in the darkness. Their cool temperatures are the key to their nature. Unlike the fiery cores of true stars, the interiors of brown dwarfs are only hot enough to briefly fuse deuterium, a heavy isotope of hydrogen, or in the very smallest ones, just lithium. This feeble nuclear activity quickly sputters out, leaving them to slowly cool and fade over billions of years, radiating only the residual heat from their gravitational collapse. They are, in essence, eternal embers from a fire that never truly caught. Studying this specific binary pair is like finding a rare double specimen in a cosmic laboratory. Their gravitational dance around each other allows astronomers to precisely measure their masses, a critical piece of data that is often elusive for such faint objects. Knowing their exact mass and temperature helps to calibrate the entire theoretical model for how stars and planets form. These brown dwarfs represent the lowest mass outcome of the star formation process, the dividing line where a collapsing cloud of gas decides it would rather be a failed star than a true sun. Their existence challenges our definitions and forces us to ask where a giant planet ends and a star begins. Are they overgrown planets that formed on their own from a tiny gas cloud? Or are they underachieving stars that were starved of material during their birth? This binary system provides a unique test case. By observing how they interact and comparing their properties, we can refine our understanding of the formation mechanisms that operate across this murky boundary, shedding light on the faintest, most common, and most mysterious objects that populate not just the Tadpole Galaxy, but every corner of the universe. A faint, all-encompassing light permeates the halo of the Tadpole Galaxy, a ghostly luminescence with no clear source. This anomalous diffuse light is our 42nd strange object, a soft glow that blankets the galactic outskirts, a cosmic background hum that stubbornly resists explanation. It is not the sharp, collective light of visible stars, nor the warm infrared glow of cosmic dust. This is something else entirely, a pervasive sea of photons whose origin remains one of the galaxy's most profound mysteries. Where is all this faint light coming from? The leading theory points to a vast, unseen population of stellar ghosts. The halo could be swarming with countless ancient white dwarfs, the burned-out cores of long-dead stars. These cosmic cinders have cooled over billions of years, fading to such a dimness that they are impossible to detect individually with our current telescopes. Yet, if their numbers are immense enough, their collective, feeble glow could add up to the widespread light we see, like a galaxy of 1 trillion dying embers. Another haunting possibility involves a staggering number of rogue planets. These are worlds torn from their parent stars, now wandering the galactic darkness alone. If the Tadpole's halo contains trillions of these frozen, nomadic worlds, their dark surfaces could reflect just enough of the galaxy's general starlight to create the faint, uniform glow. This would be a population of worlds so vast it defies comprehension, a hidden archipelago of frozen Earths adrift in the interstellar void. but the most revolutionary explanation points to the very fabric of the dark matter halo itself. What if this light is not from normal matter at all, but from the decay of hypothetical dark matter particles? Certain theoretical models suggest that these particles could be unstable, slowly decaying over eons, and in the process, releasing a faint drizzle of photons. If this is true, then the diffuse glow is not a side effect of the galaxy, but a direct signal from its primary substance. We would be seeing, for the first time, the slow and steady fading of the universe's shadow material, a gentle radiance from the invisible scaffolding that holds the galaxy together. Each explanation paints a radically different picture of the tadpole's hidden structure. Is its halo a graveyard of dead stars, a realm of orphan planets, or a reservoir of decaying dark matter? This faint light is more than a curiosity. It is a potential window into the galaxy's true mass and its deepest history, a subtle whisper that might finally reveal what the darkness is made of. A cosmic cannonball of searing gas is racing toward the edge of the Tadpole Galaxy. This 43rd strange object is a hypervelocity gas cloud, an immense structure of ionized particles moving so fast it is on a trajectory to escape the galaxy's gravitational pull forever. Unlike the cold, dark hydrogen clouds that drift in solitude, this one is brilliantly lit and fiercely hot, a tempest of energized matter fleeing its birthplace. Its speed is the key to its story, a velocity that can only be explained by a truly explosive origin. By tracing its path backward across the galaxy, astronomers have pinpointed its source to a ferociously active stellar nursery, a region where thousands of massive stars are being born in a short, violent burst. This is the engine that launched the cloud on its one-way journey into the void. The mechanism is a phenomenon known as a galactic wind. Within that crowded stellar factory, the combined fury of countless stellar tantrums creates an unstoppable outward pressure. The most massive stars pour out hurricanes of charged particles, their stellar winds blowing with the force of a million suns. Then, when these short-lived giants die, they do so in spectacular supernova explosions. Each detonation sends a devastating shockwave slamming into the surrounding gas. The cumulative effect is like a continuous, cosmic blast furnace. The stellar winds and supernova shocks work in concert, piling pressure upon pressure until the surrounding gas can no longer be contained. It bursts free, a superheated wind flowing out from the galactic disk, carrying vast quantities of material with it. This particular cloud is a massive clump within that larger galactic exhalation, a bubble of gas that was caught in the flow and accelerated to its incredible speed. The implications of this escape are profound. This wind is a primary way that galaxies regulate their own growth and evolution. By ejecting this gas, the starburst region is effectively blowing away its own future fuel supply, limiting how many more stars can form there. It is a self-regulating cycle of creation and destruction. Furthermore, this wind is chemically enriching the space between galaxies. The cloud is not just hydrogen, it is laced with heavy elements like oxygen, carbon, and iron, forged in the hearts of the very stars whose deaths propelled it outward. As this cloud travels into the intergalactic medium, it will eventually disperse, seeding the cosmic voids with the elemental building blocks for future generations of stars, planets, and perhaps even life. This hypervelocity cloud is more than an escapee. It is a delivery vehicle, carrying the products of a galactic firestorm into the vast, waiting darkness. A predictable rhythm of destruction governs a distant stellar partnership. This 44th object is a recurrent nova system, a celestial time bomb that detonates with a regularity that borders on the mechanical. It consists of two mismatched stars locked in a close, fatal embrace. One is a white dwarf, the Earth-sized, super-dense core of a dead star, and the other is a normal, hydrogen-rich companion, much like our own Sun. Their proximity is the key to the cycle of violence. The white dwarf's intense gravity acts as a cosmic thief, relentlessly pulling a stream of hydrogen gas from the outer layers of its partner. This stolen material does not fall directly onto the white dwarf's surface. Instead, it accumulates in a sprawling, ever-growing accretion disk, a swirling reservoir of volatile fuel. For years, the system remains quiet, with only this silent theft marking the passage of time. The hydrogen gas slowly rains down from the disk onto the white dwarf's incredibly hot and dense surface. It settles into a thin, degenerate layer, compressed by the star's immense gravity. This is the calm before the storm, a period of deceptive tranquility as the pressure and temperature at the base of this hydrogen ocean climb to a critical breaking point. When the conditions finally cross a nuclear threshold, the entire accumulated layer of hydrogen ignites at once. This is not a gentle burn, but a runaway thermonuclear explosion that rips across the white dwarf's surface. In a cataclysmic flash, the system brightens by a factor of 10,000, outshining millions of its stellar neighbors for a brief, brilliant period. The accumulated hydrogen is blasted into space in an expanding shell of hot gas. And then, the cycle begins anew. The white dwarf, largely unharmed by the surface explosion, resumes its theft, patiently gathering fuel for its next outburst. What makes this specific system in the Tadpole Galaxy so extraordinary is its impatience. While most recurrent nova have cycles lasting decades or even centuries, this one erupts with an unusually short recurrence time, detonating again after only a handful of years. This frantic schedule points to a voracious white dwarf. It must be exceptionally massive, nearing the theoretical limit of stability known as the Chandrasekhar limit. A more massive white dwarf has a stronger gravitational pull, allowing it to siphon material from its companion at a much higher rate. It builds up the critical mass of hydrogen needed for an explosion far more quickly than a less massive one could. The companion star also plays a role, likely being a bloated, evolved star that is particularly generous with its outer layers, providing a rich and steady flow of fuel for the thief. This short cycle makes the system a precious natural laboratory. Astronomers can observe the entire process from quiescence to eruption and back again within a human lifetime, testing models of thermonuclear explosions and mass transfer with unprecedented detail. Each eruption is a controlled experiment in stellar physics, a chance to watch a star die a little, over and over again, in a brilliant, repeating flash. Two dense, brilliant islands of stars drift in the emptiness far beyond the Tadpole Galaxy's main disk. These intergalactic star clusters, our 45th and 46th strange objects, are celestial orphans, flung into the void during a long-ago gravitational cataclysm. They are not full galaxies, but incredibly dense and ancient globular clusters, each containing hundreds of thousands of stars bound together in a tight, spherical swarm. Their current location, deep within the tadpole's long tidal tail, marks them as survivors of a violent expulsion. They are the sole visible remnants of a smaller galaxy that was torn apart and digested by the tadpole billions of years ago. During that ancient merger, as stars and gas were ripped from the victim galaxy and stretched into the spectacular tail we see today, these two clusters were likely the galactic core's most resilient components. Their immense gravity allowed them to hold together as individual units, even as their parent galaxy was shredded around them. Now they orbit not within a galaxy, but around it, tracing wide, lonely paths through the intergalactic medium. Their isolation makes them perfect tracers of the tadpole's history. By calculating their precise orbits and velocities, astronomers can rewind the clock, tracing their paths backward to pinpoint the exact moment and location of the original collision. It is a form of celestial forensics, where these two star clusters act as silent witnesses, their trajectories providing a timeline for one of the galaxy's most formative events. Their very existence confirms that galaxy growth is a messy, carnivorous process, and that even in the aftermath of destruction, the most tightly bound stellar families can endure, becoming permanent, orbiting monuments to a past cosmic trauma. Even the most voracious black hole can have a table that wobbles. A stellar mass black hole in a binary system here is feeding from an accretion disk that is not flat and orderly, but warped and precessing like a spinning top starting to fall. This warped disk is our 47th strange object, a cosmic gyroscope gone haywire right at the edge of oblivion. The disk itself is a vast, swirling river of superheated gas stolen from a companion star, but its shape is profoundly wrong. Instead of lying in a single, flat plane like a vinyl record, it is twisted, with its inner regions tilted at a different angle than its outer edges. This entire distorted structure is slowly precessing, meaning its tilted axis of rotation itself slowly sweeps around in a circle, a ponderous cosmic wobble that takes days or weeks to complete a single cycle. We cannot see this wobble directly. Instead, we infer it from the rhythmic, lighthouse-like flicker of the system's X-ray emissions. As the warped disk precesses, the inner, hottest part of the disk, which is ferociously bright in X-rays, periodically turns its brightest face toward us and then away. From our distant vantage point, this creates a regular, repeating pattern of brightening and dimming, a telltale signature of a wobbling platter of doomed matter. But what force could possibly warp a structure governed by such immense gravity? One powerful culprit is the spin of the black hole itself. If the black hole is rotating rapidly, it drags the very fabric of spacetime around with it, an effect known as frame dragging. This twisted spacetime exerts a torque on the inner part of the accretion disk, trying to pull it into alignment with the black hole's own equator. If the outer disk remains fixed in a different plane, perhaps by the orbital motion of the companion star, the result is a battle of rotational forces that twists the entire disk into a warped shape. Another potential artist is intense radiation pressure. The very center of the accretion disk, where gas is hottest and brightest, can shine with such ferocious intensity that its own light pushes back on the incoming gas. This radiation can be so powerful that it puffs up the inner disk, causing it to cast a shadow or exert pressure that physically bends the outer disk, creating the observed warp. This warped disk is far more than a cosmic curiosity. It is a precise probe of the most extreme environment imaginable. By carefully measuring the timing and pattern of the X-ray flickers, astronomers can map the warp structure and calculate the precession rate. This data, in turn, allows them to measure the spin of the black hole itself, a fundamental property that is otherwise nearly impossible to determine. The degree of warping reveals the balance between the black hole's gravitational might and the intense pressure of its own radiation. It is as if the wobbling disk is a diagnostic instrument, sending back encoded signals about the physics of spacetime just outside the event horizon, a place where the normal rules of the universe break down and our understanding is pushed to its absolute limit. A vast, glowing cavity of hydrogen gas blooms within the Tadpole Galaxy, a supershell so immense it could swallow entire star systems. This is our 48th strange object, a celestial bubble hundreds of light years across, its walls shimmering with the energy of countless stellar deaths. It is not the remnant of a single explosion, but a cumulative structure, a fossilized record of violence written on the interstellar medium. The shell's sheer scale is the first clue to its origin, a size that could only be forged by the coordinated fury of an entire generation of stars. Imagine a crowded stellar nursery, a region where dozens of massive, short-lived stars were born in a tight cluster. These stars do not live quiet lives. From the moment of their ignition, they rage against their surroundings, emitting powerful stellar winds that stream outward at millions of miles per hour. This is a constant cosmic gale, blowing for millions of years and slowly pushing the surrounding gas outward. Then, one by one, these stellar titans reach the end of their brief lives. They do not go gently. Each one explodes as a supernova, a cataclysm that unleashes a shockwave of unimaginable force. The combined effect of these repeated detonations, coupled with the unrelenting pressure of the stellar winds, acts like a cosmic snowplow. It sweeps up the surrounding hydrogen gas, compressing it into a dense, glowing shell that expands outward for eons. This is stellar feedback on its most dramatic scale, a process where stars themselves reshape the galaxy that gave them birth. The supershell is a self-regulating engine. By blowing this gigantic bubble, the star cluster has effectively cleared its own neighborhood. It has pushed away the very gas and dust that could have collapsed to form the next generation of stars, temporarily halting creation in that region. The galaxy itself is controlling its own growth, but this act of destruction is also an act of creation. The expanding shell is not a perfect, smooth sphere. As it plows through space, it can encounter other, smaller clouds of gas. The immense pressure of the collision can trigger a new wave of star formation within the shell's own walls, igniting a brilliant ring of new stellar nurseries. This single structure, born from death, can therefore become the architect of new life, a stellar parent forged from the final breaths of its predecessors. This supershell is a monument to the cycle of cosmic life and death, a visible echo of the power that stars wield over their galactic home long after they are gone. A profound emptiness shadows the Tadpole Galaxy, a satellite of almost pure gravity. This 49th strange object is a dark galaxy candidate, a massive knot of dark matter whose presence is felt but not seen. It reveals itself only by its ghostly tug on the visible matter around it, subtly distorting the orbits of a sparse handful of stars that drift through its domain. These stars are not native to the object. They are merely passing through its immense, invisible gravitational field, their paths warped as if by an unseen hand. The sheer concentration of mass required to cause this distortion is staggering. Yet when astronomers point their most powerful telescopes at this region, they find almost nothing. There are no swirling spiral arms, no brilliant nebulae, only a faint, diffuse smattering of ancient suns, far too few to account for the powerful gravity that holds them. This object appears to be a galaxy in which dark matter has overwhelmingly won, a place where the normal process of gathering gas and igniting stars was somehow stifled almost completely. Its existence is a crucial test for our fundamental model of the universe, known as the Lambda-CDM model. This model predicts that the cosmic web of dark matter should be littered with countless small clumps, miniature halos that serve as the building blocks for larger galaxies. Yet, when we look around our own local universe, we find far fewer small, visible satellite galaxies than the theory suggests. This is known as the missing satellites problem. Dark galaxy candidates like this one could be the solution. They are the predicted clumps, but they fail to attract enough normal matter to light up with stars. They are the dark, silent majority of galactic building blocks, forever lurking in the shadows. The challenge, of course, is confirmation. How you prove a galaxy exists when you cannot see it? Astronomers must become cosmic detectives, piecing together indirect evidence. They meticulously map the motions of every single star in the vicinity, building a velocity map that reveals the underlying gravitational landscape. They search for the faintest whisper of neutral hydrogen gas, a possible trace of the little normal matter it managed to capture. They even look for the subtle flickering of distant quasars, whose light might be magnified as it passes through this invisible object's gravitational lens. If confirmed, this dark satellite would do more than just solve a cosmological puzzle. It would reveal a universe where dark matter can dominate structures on every scale, from the vast halo of the Tadpole Galaxy down to these small, isolated clumps. It forces us to ask why some dark matter halos blaze with billions of stars, while others, like this one, remain forever dark and dormant, the silent, unseen foundations upon which the visible universe is built. The final object in our cosmic collection is a brilliant quasar beaming from the edge of time itself, its light warped and multiplied by the tadpole's gravity into 4 perfect, shimmering mirages. This distant, lensed quasar is not one of the galaxy's own residents, but a beacon from the ancient universe, a supermassive black hole feasting at the heart of a primordial galaxy so far away its light has traveled for billions of years to reach us. The Tadpole Galaxy, acting as a colossal natural telescope, has bent this light around its dense core, splitting the single point into a delicate cosmic cross, an effect known as an Einstein cross. Each of the 4 images we see is a slightly different path the light has taken, a separate journey around the gravitational well that results in a breathtaking optical illusion. This gravitational lensing is more than a beautiful trick of physics. It is one of our most powerful tools for cosmic exploration. The amount of bending depends directly on the total mass of the lensing galaxy, providing astronomers with an incredibly precise way to weigh the tadpole, including all of its dark matter. Even more profoundly, the lens magnifies the quasar, making it appear dozens of times brighter than it truly is. This allows us to study the quasar's immediate environment in exquisite detail, to analyze the composition of the gas whirling around its black hole, and to observe the physics of accretion in the universe's infancy. We are essentially using the tadpole as a ready-made observatory, a giant lens that brings the distant, faint early universe into sharp focus for our telescopes. The 4 images also act as a cosmic clock. Because each light path is a slightly different length, any flicker in the quasar's brightness will appear in each image at a slightly different time. By meticulously measuring this time delay, scientists can perform a remarkable calculation, triangulating the geometry of the entire system to derive an independent measure of the universe's expansion rate. This single, lensed object becomes a key that can unlock fundamental constants, a natural laboratory for testing our deepest cosmological models. As we conclude our journey through these 50 strange objects, this distant quasar offers a final, profound reflection. The Tadpole Galaxy is not merely a collection of mysteries. It is an active participant in the quest to understand the cosmos. It bends light, magnifies the distant past, and reveals the invisible scaffolding of dark matter. It is both the subject of our investigation and the very instrument we use to see beyond it. A reminder that sometimes, to gaze into the deepest reaches of space, we must first look through the lens of another. Our journey through 50 cosmic oddities is complete, a tour of rogue black holes, stellar zombies, and natural lasers that defy simple explanation. Each of these strange objects, from the flickering heart of the supermassive black hole to the lonely wanderings of the isolated magnetar, serves as a profound reminder. The universe operates on a scale of grandeur and peculiarity that consistently outstrips our wildest imaginations. These are not mere astronomical curiosities. They are the fundamental drivers of discovery, the cosmic puzzles that force us to question, to rethink, and to push our instruments and our intellects to their absolute limits. Every mysterious signal and every warped image is a direct challenge, an invitation to look deeper and understand more. This relentless pursuit of knowledge is the very soul of astronomy, a field forever humbled and energized by the sheer weirdness of the cosmos. As you reflect on this voyage, we would love to hear which of these 50 strange objects captured your imagination the most. Was it the deceptive supernova impostor, the ghostly dark galaxy, or the brilliant lensed quasar from the edge of time? Share your favorite cosmic mystery in the comments below. And if you are ready for more deep space discoveries, be sure to subscribe for our next journey.